Hello, Jeff Disher here again. Today I'm going to talk about emulators and virtual machines and what some ideas around virtualization and just-in-time compilation and emulation are like. So first of all, what we're going to be talking about today is I'm going to go through a basic definition I'm going to use of emulation versus virtualization. In general, these terms are kind of confused and kind of conflated together, so I'm going to talk about what I mean when I'm using them in this kind of talk. Also, I'm going to define what's meant by host and guest. You'll see these terms come up a lot if you look at anything about emulators or virtualization environments. So that's something that you'd need to know. Also, going to talk about why you'd emulate something. There's a lot of overhead and extra complexity added when you're emulating or virtualizing an environment. So it's a question of, okay, well, why would you use an emulator if it's going to slow things down or be more difficult to create? So then, because we're talking about CPU emulation, I'm going to be talking about how physical CPU operation actually works, like if you kind of look at a high level what it's actually doing, and then contrast that with software CPU emulation. So if you're actually pretending you have a CPU in a piece of software, what that would be like. And closing off with a quick talk on JIT, or just-in-time compilation, because that's a way of improving performance in emulators, and there's some neat possibilities there. So emulation versus virtualization. Now I'm going to use what's kind of an unofficial distinction because sometimes these terms get thrown around a lot and they seem very, very similar. Sometimes, depending on who you're talking to, you get different terms used to mean the same thing. So what I'm going to talk about is emulation is going to be making one thing imitate or emulate another, but it's going to be a different thing. So you're going to have one CPU, like an x86, emulating a PowerPC or something like that. They're pretending to be something totally different. Virtualization is, I'm going to kind of draw this distinction where I'm saying it's presenting an external behavior adapted from its native form. Now, what I mean by that's kind of over wordy and a little weird, but what I mean is a simple example would be, say, maybe you want to virtualize a hard drive or something, and you do that by saying, okay, well, we'll just take a part of the hard drive and tell the virtualized environment that that's an entire hard drive. So it's still just the same thing. It's just kind of a different way of exposing it. We're not really changing what it is, just how it's accessed externally. And so to avoid confusion, this talk is only about doing emulation in software as well, not talking about any kind of specialized hardware or coprocessor cards or anything like that, which are sometimes used to make emulators faster. So something to talk about as well that's important is a distinction between host and guest. Now, a host is the thing that's running the emulator. It's your actual computer where you have the emulator or virtualizing software actually running as just a program. Now, the guest is what's actually being emulated. So the emulator, because it's going to be a piece of software that's pretending to look like a CPU, it's running on your host. But whatever is running on that fake CPU is going to be the guest. Because remember, it's pretending to be a CPU, and it can run programs for that other CPU. It runs those in what's called a guest environment. That's a distinction we use so that you don't get confused about which CPU is which. So there's always host and guest. And these could be the same kind of machine. There's reasons why that happens in a lot of virtualization situations, for example. But you don't see this as often in emulation. Sometimes you do, and I will talk about that very shortly, or for a short bit right at the end. And also, something which is possible, although this is very uncommon, is the host might be a guest of another host, right? You can have, because your guest is emulating a CPU, well, that emulator could also be running an emulator as well. So you could have sort of one host with a guest on top of that and a guest in that, and so on, and you kind of get this weird, it's turtles all the way down phenomenon, and that's not very common because there's a lot of overhead in running one of these emulators. So if you're running an emulator on top of an emulator, you're just kind of magnifying that overhead. So it's not something you want to do. You'd only end up doing that by accident, generally speaking. So given that there is an overhead associated with emulators, why would you do that? Why not just run it on the hardware that you want? Why would you need to have this extra complexity running there? And there's a bunch of reasons. First of all, maybe the real device isn't available. You have to emulate it because maybe it's too old. You get things like, for example, a lot of people have things like old game system emulators on their computers these days where they run old games and stuff like that. It's because they don't have that device anymore. It's too old, it's hard to get one now, things like that. So they can run it in software. And because there's been decades of time that have passed within there, the performance is actually going to be very good. So it's not going to be, the overhead isn't going to really hurt you. But the other interesting reason is that you might be trying to prototype something new. This is something which you see come up when you're looking at companies that build CPUs or design CPUs. If they're coming up with a new one, well, they don't have it yet. So how do they make sure that it's going to solve the problem? Well, they write a piece of software, which is the emulator, for the kind of hardware they want to build. And then they can see how it's going to work, what are some sort of gotchas they should change now, because otherwise they'd have to wait until they've actually gone and designed the whole hardware itself and actually built the silicon wafers and actually cut them up and put them in real hardware, and then suddenly they'd realize, oh wait, there's something missing or something we should have thought about more. So this allows them to test it faster. And the other reason is, another reason is the behavior might not be feasible in hardware. So you might have high-level capabilities, like things like, oh, I want to have memory and do something with that, or I want to be able to ask for other kinds of resources like that. Well, your CPU doesn't do that. It's given to you by your other supporting components of your operating system. So if you actually, maybe you could build something that's an instruction set, a fake instruction set that has that, and then you just run that on an emulator. This is similar to what things like Java do, actually. And also there's portability, which again comes down to things like Java and JavaScript, where you're not worried about it being the perfectly tuned program for a piece of silicon. You're just saying, I just want to make sure that the description is concise and well-defined so that we can run it somewhere else. So then you can actually move the program to a different piece of a different computer altogether and have it run the same way, because you're using an emulator to actually perform these operations you need in a way that's going to be the same no matter what the actual hardware is. So it's very useful for things like that. And we see a lot of that today, so you can tell it's an important concept. So now that we know, okay, why you'd want to do this, how does it actually work? What's the difference between physical CPU versus an emulated CPU? Like, it seems like it would be kind of almost this magic to make one work like the other. And it does seem that way until you think about just kind of from a very high level. What are the basic operations a CPU needs to perform? And then you realize, okay, well, I know how to make software can do those things too. And that's when you start to realize that you can actually build this. So a physical CPU, it has internal state in pieces of silicon called registers. And then it has a program stored somewhere in memory. And it also has memory that it uses for storage and things like that. So what it does is, to execute one instruction, the CPU is going to just kind of read the program out of memory, and then it'll execute it by changing state, either changing its registers or changing the storage it's using in memory, something like that. And then it just advances to the next instruction. So there's nothing really magical about this. It's sort of, okay, go get the next thing, look at it, determine what to do that thing, like change into that state that it tells me to change into, and then go get the next thing. Well, this is what a lot of software loops look like too, so you could just do it that way. So in an emulated CPU, you can have an internal state maintained in memory. So in software, you don't really have registers. Like you might have an optimized way of doing this where you try and exploit the registers of the actual CPU you're using, but in general, you don't have things like that to think about. So you talk about, okay, there's going to be pieces of memory that I'm going to use to store the internal state of the CPU. And memory is going to be basically the same thing, except it's going to be segregated, and there might be some other gotchas. What I mean by segregated is you're going to want to make sure that the guest memory is not kind of intermingled with with the memory that the emulator itself is actually running in, because otherwise it's possible that you could end up having problems like exposing security issues, because the program you're emulating might be able to change what the emulator itself is doing to kind of escalate its privileges, things like that. So you don't want it to do that. So usually you have segregated memory. And also, you have to be worried about what's called endian. Now, endian basically just comes down to when you're putting data into memory, you need to think about, okay, well, do I put the bigger end first or the smaller end first? And so you have big and little endian. And that's something that a bunch of different CPUs do differently. So you need to make sure that when you're actually saving out to memory inside one of these environments, that you take that into account, because otherwise you might expose problems in the software you're trying to emulate, because now memory works slightly differently, and they're going to be confused. So there's some problems that can expose that difference, so you need to make sure you're doing it right. And then how you execute one instruction is kind of similar. You read the next instruction out of the program in memory, same way it would in the physical CPU, and then you decode the meaning. Now this is really the only thing that's going to be different. In a physical CPU, decoding a meaning is something done kind of in parallel on the actual transistors, whereas in software you'll have some sort of big decision-making tree of some sort that's actually trying to decode what this means and get all the data that's required to execute that instruction. So this is where sort of the only real difference is. Once you've decoded the instruction, then you change state just like the physical CPU would. You're just doing it on pieces of memory instead of pieces of silicon. And then you advance to the next instruction. So it works very much the same way, aside from just some details about how this decoding is done. But really it's the same process. You're just walking through memory, reading one instruction, changing in response to that, and then getting the next instruction. So they kind of map from one to another very nicely. It's not really as magical as it kind of seems at first. And so one of the things I want to talk about, because we've talked a lot about emulators and what they do and all that, but there's a lot of performance problems with that. Like trying to actually do that decoding, that takes a lot of instructions. But the CPU itself would do that immediately. Like it would take like 1 or 2 cycles to do that. It would be really, really fast. So, okay, you're looking at something that's going to be a lot slower. Well, how can we make that faster? We'll use what's called just-in-time compilation. And what that means is it's going to actually recompile the program you're trying to run in your guest environment to be a program for your host environment, and then it'll start executing that directly. So it's a compiler that actually runs just in time. It's not like an ahead of time or static compiler where you compile it when you write the program. Here you're actually compiling when you run the program. So it's kind of it's just a different point where you do this, but that has some implications. It's similar to a concept called code morphing. This is something you'd see in like a Transmeta-Crusoe processor. They had what was basically just a simplified JIT that they called code morphing, which would actually run to change x86 into Transmeta instructions. So what you're doing is you're going to compile guest instructions to the equivalent instructions for host. Now this is, there's a lot of complexity in terms of how you do that, how you decide when to do that, and how many instructions you look at once, because maybe you can compile it better than it could have even been compiled originally, because your processor is different and can do some things that are more convenient. So it's a very large area. There's a lot of discussion that still goes on in this because it's a big deal, and there's lots of opportunity for some real cleverness and some real great wins. So this gives you a huge performance increase, because now you're not having to do that, decode every instruction. Now you're actually just going to do that once when you do the compilation, and then you'll just get your host CPU to actually do all the heavy lifting for you, because that's what it's good at. So this is a really important thing when you look at emulators, and especially virtual machines. They get a lot of benefit out of this. And something that's a really kind of exotic and interesting example of how to think about this is your host and guest might be the same thing in a JIT. There's something that some people call the promise of JIT, which is that a just-in-time compiler, because it knows what you're actually doing, it actually could do a better job of compiling your program than the compiler that you run when you're writing it. Because that compiler doesn't know what you're going to do. It just knows, okay, this is what you said. But it turns out that in reality, that thing that looked important is never actually done. So we'll actually optimize the code differently to actually account for what you do use this for, not just what it looks like it meant. So this can give you certain kinds of performance wins, and it's not just hypothetical. This actually does work. Hewlett-Packard had something called Dynamo, which ran on their PA RISC hardware back quite a while ago now. And that actually did show some noticeable performance wins in a bunch of benchmarks. So it's not just something like pie in the sky sort of, yeah, you could do this. No, it actually works. People have actually created real software that was actually higher performance because of this. So it's a really interesting area, and there's still a lot of talk about this. And because of things like Java and JavaScript being so common, you're actually seeing the need for JIT and the JIT-related discussions going kind of everywhere now. So it's a really kind of a hot topic, but also really, really neat because there's lots of opportunities in it. So I hope that kind of gave a basic understanding of what an emulator is and why you'd use it and how it works generally. You can post comments here if there's any questions, or send me an email here to either ask about this video, or if you want to suggest something else, because I'm always interested in seeing what people want to hear, because I like talking about this stuff. So anyway, let me know what you think, and subscribe if you're liking these. Thanks. Bye.